All right, greetings everyone. Welcome to the first part of the video for section 3.7. Moving on to studying a new type of function that we haven't looked at yet. We'll be talking about something called rational functions. All right. So we're going to start off by doing some investigation with a couple of our toolkit functions. So we were looking at properties of both the reciprocal and the reciprocal squared functions. Okay. And you'll see on the slide here, it says some stuff we're going to investigate about them. I will get to that in a second. We're going to go to our graphing calculators here. And we'll start by graphing the reciprocal function. So I'll go into my y equals, do my 1 divided by x. Remember the reciprocal function is 1 over x. If I graph that now, we see that it has something that looks like this. And on a lot of your calculators, it may look like at this point or this point, the graph just ends, but we know from our study that that's not what happened. It actually continues on up like this and down like, not like any of those things I just did. So it continues on like this, all right? And the first thing we were asked to find, or first things we were asked to find on those, or on that slide we just looked at, are the horizontal intercepts and the vertical intercept of this function. Now recall horizontal intercept, that's where it intersects the horizontal axis. But if you look along the horizontal axis here, okay, this graph never actually intersects it. Now it might look like it does, because if you kind of follow the graph here, it looks like it comes up and gets closer and closer and closer and then must eventually either cross it or hit it or something like that. But that's actually not what happens. Okay, the graph from both the top and the bottom will come up or down to the horizontal axis, get closer and closer, but never actually touch it. So there's actually no horizontal intercepts here. And a similar thing is true of the vertical intercepts. So if we look at the vertical axis, so this one here, okay, also coming from the left and the right, okay, these graphs, whoops, are going to get closer and closer to that vertical axis, but never actually touch them. Okay, so the vertical intercepts there are also D and E. All right. The next thing we're going to talk about then are what are called asymptotes. Okay, an asymptote is generally a line that a graph will get closer and closer to, but never cross. And there's an asterisk on that never cross. Okay, sometimes a graph might cross an asymptote, but it only crosses it like 1 or 2 times, and generally, other than that, it just gets closer and closer to it and never crosses it. Okay, and we'll see more examples later on of what that means. All right, so let's look first for what's called a vertical asymptote. So this would be a vertical line that I could draw in the picture here. Now the graph of the function gets closer and closer to, but never actually crosses. And hopefully you see right away, we were just looking at one, right? If I draw a vertical line right along the vertical axis there, from both the left and the right, the graph is getting closer and closer, but never actually crossing that. And we know from our studies of lines, and because the equation here is f of x equals 1 over x, that this vertical asymptote here is going to be at the value x equals 0, because for every point along that line, the value of x is 0. And then let's now look at horizontal asymptotes. Okay, so those would be horizontal lines, or a horizontal line that the graph gets closer and closer to from either the top or the bottom, but never crosses. And again, just a few minutes ago, I had that line, right? It was one that was right here along the horizontal axis. And we know that any horizontal line like that will have the form of like f of x or g of x equals something. It's a constant function. In this case, because it goes along the horizontal axis, it would be g of x equals 0. Okay. All right. One more thing with this. Let's look at the long run behavior. So what happens in the graph as the input values get really, really large or really, really small. So I'm going to look at as x goes to positive infinity here. What is f of x going towards? And in the past, when we've done this, the answer has been something like positive or negative infinity. But notice if we trace the graph here, right, and follow it along as it goes out to the right, notice that the output values are getting closer and closer to that horizontal asymptote value. So we see that in this case, f of x is going towards 0. Similarly, if we go the other direction, so if we have as x goes to negative infinity, look at what the outputs the f of x's are going towards. And we'll trace going this way now. We'll notice we see a similar thing, right? The graph is getting closer and closer to that horizontal asymptote, which is at g of x equals 0. So we see the outputs are getting closer and closer to 0, like that. Okay, so that's just some what we call graphical analysis of our reciprocal function. Now let's look at what's the same and or different for the reciprocal squared function. So recall that the reciprocal squared function is the one whose equation is 1 over x squared. So go back to my graphing utility here. I'm going to put x squared in the denominator. And we graph that one. See that it looks something like this. And let's again do this same analysis. So horizontal or vertical intercepts. Well, again, we see that the graph is coming down and getting closer and closer to the horizontal axis, but never crossing it. It also goes up and gets closer and closer to the vertical axis and never crosses it on the left-hand side. And does the same thing on the right. So we see that just like with the reciprocal function, there are no horizontal or vertical intercepts here. We also see that the vertical asymptote is still going to be at that value x equals 0 right there on the vertical axis. Horizontal asymptote is still at the value g of x equals 0 at the function there. And we see the same long run behavior, right? As x goes towards positive and negative infinity, those outputs are getting closer and closer to 0. Okay. All right. Well, let's go back to our slides then. And what we were just looking at, both the reciprocal and the reciprocal squared function, those are both examples of what are called rational functions. Okay, and this is what section 3.7 will be about. Now notice in that word rational, you see the word ratio. So rational functions are terms that can be, or functions that can be written as a ratio of two polynomials. Okay, and that word ratio, it's kind of a fancy word for fraction. So we're really looking for functions that can be written as fractions of two polynomials. So for example, x squared plus x plus 3 over x cubed minus 7. That's a rational function. It's a ratio of two polynomials. In the case of the two we were just looking at, f of x equals 1 over x, and f of x equals 1 over x squared. Those are both examples of rational functions. Okay, you can see on the bottom for sure, x and x squared are both polynomials, and then 1, believe it or not, is a polynomial because we can think of that as 1 times x to the 0. Because anything to the 0 power is 1, so 1 times 1 is 1. So those are all the same thing. All right. Now, an interesting thing or a common property of rational functions are vertical asymptotes and horizontal asymptotes for that matter. And what we want to do is try to figure out on this function here, f of x equals x squared minus 4 over x squared minus 7x minus 8. If there's a way, just looking at the formula there, that we could figure out where the vertical asymptotes are. And before we do that, we're first going to graph this function. So I'll go back to my graphing calculator. Okay, I'm going to clear out the function I had in there and put in the one we're just looking at. Now, I want to be very careful about the way we enter this because it was x squared minus 4 all over x squared minus 7x minus 8. And so we want to make sure that what we put in the calculator recognizes that. So in order to do that, I'm going to put parentheses around the top. So I have x squared minus 4. Okay, so that's my whole numerator. That's in parentheses. Divided by, and I'll put parentheses around my whole denominator. So I have x squared minus 7x minus 4. Okay? Now it's really important you do that because if you put it in like this, okay, x squared minus 4 over x squared minus 7x minus 4, without the parentheses, you will not get the correct graph of what I'm about to show. Because this thinks, if you put it in the calculator like that you only want those two divided, which is not what you want, right? You want this whole thing divided by this whole thing. Okay, so once we get that put in, let's go ahead and graph it. Graph it, wrong button, Cody. There we go. Okay, and we get a function that looks like that, which I know is a little weird. And sorry, something looks off. Let me just double check. This should have been a minus 8 here, not a minus 4. I apologize for that. There we go. That looks better. And let's look and see if we can identify where the vertical asymptotes are. Well, it looks like one is here at x equals -1. And it looks like maybe there's another one at 2, 4, 6, maybe at +8 here. Right there, maybe. Okay. So it looks like we should have them at x equals 1 and x equals +8. Let's go back to our slide. So again, we think that these would be at x equals +1, or excuse me, -1, and x equals +8. Is there any way we could get that from the formula here? Well, watch this. Watch what happens if we factor the numerator and the denominator. So on the top, that x squared minus 4, recall that's our difference of two squares, so like our a squared minus b squared. So this could become x minus 2 times x plus 2. On the bottom, it looks like we could factor that as x minus 8 times x plus 1. And now compare these to that formula. Do you see where they're coming from? Right, those are the zeros, or the roots, of the denominator. So notice x equals +8, x equals -1 are the things that make each of these terms, or these factors down here, equal to 0. So it looks like we can look in the denominator for the zeros of the denominator of our rational function to try to find the location of vertical asymptotes. Cool. All right, we will talk more about that in the next video. Thank you for watching.